Okay, we're going to look at some examples where we use integration to find areas of regions between curves. And so this problem says sketch the region and use an integral to find the area. But even if it didn't say to sketch the region, that would be a good idea. And even if it didn't say to use an integral to find the area, that's really what you would need to do here. Okay, so even if it just said find the area of the region between these curves, you should still start by sketching the region and using an integral to do that. Okay, so I started here with two functions that should be pretty easy to think about what those graphs look like. If there are ones that aren't as easy, remember you can use a graphing calculator to help you with the graphs here. But this first one, y equals negative x, that's just a line through the origin with slope -1. So that's pretty easy to think about what that graph looks like. Line through the origin with slope -1. This second one here is a basic parabola, y equals x squared form, that's been flipped upside down by the negative that's times the x squared and shifted up 2 units. So I would think about this function as being the same as negative x squared plus 2 when I'm thinking about that graph. Of course, you can use your graphing calculator to help you if you need help with that, but it should be pretty easy to think about the basic shape of that graph. So that would be at 2. All right, so what we're interested in here is the area enclosed by those two graphs, so the area of this region here. And so one important thing that we're going to need to know is the intersection points where those two graphs intersect. And if you've got a graphing calculator, that can help sometimes, but we're going to also talk about how to do that algebraically, just in case the answers you get from your graphing calculator turn out to be kind of ugly looking decimals. You want to be able to do this so that you can get exact values and do that algebraically. So we're just looking for the intersection points between these two function equations. So in essence, we're really solving a system of equations here algebraically. So we have a lot of methods for solving a system of equations. I would use some variation of substitution here for this particular one. So I have here y equals negative x, so I can substitute that into my other equation in place of y. So I get negative x equals 2 minus x squared, and then I need to solve for x. So you should recognize this is a quadratic equation with your x squared in here is the highest power term, and an x to the first and a constant term. So if I can get that equation equal to 0, then I can either use quadratic formula or factor. Okay, so I'm going to add x squared to both sides. So I'll have x squared minus x, and then subtract 2 from both sides. So minus 2 equals 0. This one happens to factor, but if it didn't factor, you could use quadratic formula. This factors into x minus 2 times x plus 1. And then when I set each of those factors equal to 0, I'll get x equals 2 and x equals -1. All right, so those are the x coordinates of these 2 points just by thinking about the graph here. This one has to be at x equals 2, and this one has to be at x equals -1. I may or may not need the y coordinates of those points, depending on how I set up the problem, but they're not too hard to find. I can use either of these 2 equations to find the y coordinates of those points, but my y equals negative x is maybe easier. So if I put x equals 2 into that equation, I get y equals -2. And if I put x equals -1 into my equation of my line, I get y equals 1. All right, so one important thing to do here, even if it doesn't tell you to sketch the region, would be to find these intersection points. And the reason for that is that those are going to help you set up your integral and your limits of integration. Okay, so when we first looked at developing this idea using Riemann sums, we talked about that we have these different regions, and we may choose to partition them using a delta x partition or a delta y partition. This problem is set up so that a delta x partition is better. If you think about dividing this region up into a bunch of little rectangles, right, I can partition my interval from x equals -1 to x equals 2 up into little delta x's, into little subintervals of width delta x. I can choose an x coordinate in each of those subintervals and use that to get heights of my rectangles here. And so for this one, a width of delta x partition technically that would be a delta x sub k, but in general a delta x partition. And then the height of the intervals here, or the height of the rectangles here, would be given by my function that's on top. I'm going to call that f of x. My function that's on top, evaluated at that c sub k value, minus my function that's on bottom, we'll call that one g of x, evaluated at that same x coordinate, c sub k. Okay, so this was what we looked at in the development of the idea of the Riemann sum and how we would use these definite integrals to do this. But the big deal thing from thinking back through this is to understand that you want to use a delta x partition here. So that means that we're going to use a dx integral. So when I set up these integrals, often the first thing that I set up is the differential that goes at the end. I decide whether I want a dx or a dy, and that's based on the geometry of the region. Okay, once I've set that up, then I need to make sure that everything in my integral is in terms of x. So my functions here are going to be my top function, that's f of x equals 2 minus x squared, minus my bottom function, my g of x function. Okay, I put parentheses around my f of x and my g of x here. Especially the g of x function, if you have more than one term, you have to be careful about the subtraction, that you may need to distribute that through. So this is my f of x function, top, my g of x function, which is what's on the bottom. And then my limits of integration, my a and b for my limits of integration are going to be my x values from one end of the region to the other. So that's why it's important to find the coordinates of these points, and we need the x coordinates from those endpoints. So my lower limit of integration here is going to be the smaller number on the left side. And then my upper limit of integration is going to be the larger number on the right side. Okay, so you really do need that picture in order to help you set up this integration. First of all, to think about whether you want to use a dx or a dy integral based on how you're going to partition that region. Top function minus bottom function, so you need to be able to think about the picture to see which one's on top, and then left and right limits of integration. Once you've got the integral set up, then what's after that is stuff that we've been working on for a while. So I'm going to just go ahead and do that. Tidy this up maybe a little bit before I do the integration here. I'll maybe write this as 2 minus x squared plus x. These are all pretty easy antiderivatives at this point. 2x minus 1/3 x cubed plus 1/2 x squared. And then we're going to have that evaluated from -1 to 2. All right, so we're going to take this whole function, plugging in our upper limit of integration first. So 2 times 2 minus 1/3 times 2 cubed plus 1/2 times 2 squared. So that whole function evaluated at x equals 2. And then minus my whole antiderivative here, evaluated at x equals -1. Be careful with all the minus signs and the exponents and the negatives that you evaluate -1 to a power correctly. Okay, so then you just want to go ahead and evaluate all this. I'm going to just tidy it up a little bit, but sometimes maybe getting out your calculator at this point is okay. All right, so 2 times 2, that's 4. 2 to the third is 8, so minus 8/3. 2 squared is 4, times 1/2 is 2. And then here, 2 times -1 is -2. -1 cubed is -1, times the -1/3 will make that plus 1/3. And this is supposed to be 1/2. Sorry, I wrote that down wrong. 1/2 right there. -1 squared is +1, times 1/2 is 1/2. Okay, and then maybe I distribute my minus sign through on this second parentheses here, or maybe at this point I just add all those up. But you should get 9/2 or 4.5 or 4.5 exactly. Okay, so that represents the area of that region, the true area of that region. I don't need to split it into separate integrals or worry about the fact that this second function is below the x-axis on some interval because of how we develop those Riemann sums, top, bottom, left, right, dx integral, and then from there it's just evaluating like we've been working on for a while. Okay, we'll look at some slightly more complicated examples of the same idea in the next couple videos.